Hey guys, this is going to be the lecture for Unit 11, Section 1. Today we're going to talk about energy and work, specifically more about work and what it takes to do it and the different types. All right, so work, just straight out of the book, the definition is the transfer of energy to a body by the application of a force that causes the body to move in the direction of the force. So if you've got some object and you push it some distance, you've done work. Right? The equation for work is force multiplied by distance. Keep in mind that our units here are going to have to be precise. Our force needs to be in newtons. The distance has to be in meters. So if you've got kilometers, you need to switch it back to meters by multiplying by 1,000. All right, that's going to give us work that is measured in joules. Remember when we did the egg drop that we measured joules as 1 Newton meter, and that's just the energy required to move 1 Newton, 1 meter of distance. All right, so we do that by using a couple of different types of machines. We either use levers or inclined planes. These are types of simple machines. There are 3 levers. There's the simple lever, a pulley, and a wheel and axle. So a lever is a lot like a seesaw or a teeter-totter. You've got a flat surface and something with it to act as a fulcrum. Right? A pulley just does that around a circle, and then a wheel and axle is the same thing, but the axle can spin as well. Right? An inclined plane is just a ramp. A simple inclined plane is just a wedge, is just a ramp. A wedge is 2 of those ramps put back to back. Right? So if you've got one triangle like this and you rotate it, and you take another one, you put it like this, you now have a wedge. Right? And a screw takes that inclined plane and wraps it around a cylinder or a cone. Right? Machines can change the speed or direction of a force. Right? We see that with levers, easy enough. We also can change the amount of force. So if you take a your lever and you've got a fulcrum here versus here or back here, this force is going to get changed in direction and in amount. All right, so we're going to change the direction and amount, but we're not changing the speed of that force in this case. Using a pulley or a series of pulleys as in like a block and tackle, you can change the speed as well, or you can change the force and direction again. All right, you're not going to be changing those at the same time usually. Right? And if you want to make a complicated machine or a compound machine, you just take multiple simple machines and you smash them together. Right? There's a lot of good examples in the book about that, and then there's going to be some practice problems where I have you think about some. Feel free to research, go out on the internet and look for answers. You don't have to think of them yourself. All right. Efficiency is how we measure these machines. All right. On the slide about efficiency, you'll see the equation for efficiency straight out of the book. We're going to make sure that our input and output work is in joules, not kilojoules. Right? And just like anything with percent, we're going to make sure we multiply by 100. All right? So machines always require more work than they produce. So this efficiency rating should never be over 100%. If you get over 100%, flip your output and input and see what you get. All right? That's usually what happens. And then we can also talk about the amount of change in work that machines do by talking about mechanical advantage. Right? All that text on the slide about mechanical advantage is simplified by the drawing on the next page. All right? The drawing on the next page looks a lot like this, right? Where we've got some force, I called this force B, pushing down, and the distance between the fulcrum and where the point force is, that's going to be a lowercase b. Right? This is going to be a lowercase a, and the force is going to be force at A. Right? So we've got, this can also be called force in and force out. That's what your book uses. I just like to think of it as a teeter-totter or a seesaw so that I can think about it a little easier. All right. If you need to go back and listen to that again, go ahead. Hit pause now, go back. I'm going to start doing some practice problems. Remember that you have a digital copy of the book. That's what I'm working on off of my laptop because I did not bring my book with me to do recordings. So go to page 107 and we're gonna do number 1. Hit pause, get your book out, go open the web page, whatever you need to do, and then come back to this, and you'll see me start. All right, so we've got number 1 on page 107. It reads, a couch is pushed with a horizontal force of 80 newtons and moves a distance of 5 meters across the floor. The question asks, how much work is done in moving the couch? So our equation for work is work equals force multiplied by distance. All right, work equals force multiplied by distance. So all we need to do is take those numbers out of the work problem and put them into our equation. The force is 80 newtons, our distance is 5 meters. If you do 80 times 5, you should get 400. That gives us a Newton meter. Remember that Newton meters are just joules. I want you to start putting those together, right? See that those units simplify to joules and change them accordingly, right? Number 2 asks, how much work do you do when you lift a 100 Newton child half a meter? So again, we're going to start with the same equation. Work equals force multiplied by distance. This time our force is going to be the weight of the child, 100 newtons. And we're going to multiply that by the distance we lifted the child, half a meter. So what is half of 100? 50. And that's going to equal joules. Right? I want you to try 3 and 4 on your own. So go ahead and hit pause. Do the work. I'm going to start working on it on the board. Check and see if you got the same thing I got. All right, so you saw me cross out the zeros here. I just simplified this to 4 and 24,000. And then I did 24 divided by 4 to get 6, and then I added the zeros back here. All right, that's how I did that without a calculator. 4 tells us that the force needed to lift an object is equal in size to the gravitational force on an object. That means the weight of the object, right? That's what weight is from last unit. So let's just use the weight equation for the force. So weight equals the mass times gravity on the object, right? And it tells us that its mass is 5 kilograms. Right? And then they're going to tell us that the vertical distance it gets lifted is 2 meters. Note how my weight is a lowercase w and work is an uppercase W. Make sure I can tell the difference on your work. So we're going to just put all of this here. And the distance was 2 meters. 2 times 5 is 10. 10 times 9.81 gets me 98.1. And my units are going to be joules. This one I want you to try significant figures on. So hit pause. Make sure you write your answer in significant figures. Right, we only have one significant figure here. So that's going to be this 9. So the 8 has to round it up. So this just becomes 100 joules. The rest of them, your answer should have already been in significant figures just by doing the math. All right, that is the example problems I'm going to do for work. If you need more, send me an email. Let me know. I can make more of these videos pretty easily. All right, go ahead and go to page 110 in the book. We're going to do one problem on efficiency. All right, number 5 reads, find the efficiency of a machine that does 800 joules of work if the input work is 2,000 joules. So E equals work out divided by work in times 100. So work out over work in times 100. Remember, we're expecting less than 100%. So if you get these wrong, flip them over. All right. So this says that it does 800 joules of work if the input work is 2,000 joules. So that right there tells us the input work is 2,000 joules. So the work out has to be the 800 joules. You'll note that joules cancel with our units, and we're going to left with no units whatsoever. That's what we expect with percentile answers. So put that in your calculator. 800 divided by 2,000, you should get 0.40. You multiply that by 100, it gets you to 40%. Right? These aren't that hard. You should be able to do them. I want you to try 6 and 7 on your own. I'm not going to work these out, but if you want the answers, send me an email. I will give them to you. All right, and then jog over to page 112 we're going to do 8 and 9. So 8 reads, calculate the mechanical advantage of a hammer if the input force is 125 newtons and the output force is 2,000 newtons. So mechanical advantage is force out over force in. And it's not times 100 or anything, we're just doing this. That's all. So don't make this a percent. It's going to be it should be a small number sometimes. All right, so it says the input force is 125, the output force is 2,000. Note these are forces, so our units are now newtons instead of joules, but they're going to cancel. So you do that math, you should get 16. So the mechanical advantage is a factor of 16 for this hammer. All right, 9 says find the force needed to lift a 3,000 Newton weight using a machine with a mechanical advantage of 15. So we're going to set this up the same way. 15 is the mechanical advantage. All right, and we know it needs to lift 3,000 newtons, so that needs to be the output force. All right, I want you to hit pause and try to solve for force in. This is just algebra. You can do this. All right, if you multiply both sides by force in and divide by 15, it cancels the 15 out and it cancels the force in out. So we're left with 3,000 divided by 15. All right, we know that 30 divided by 15 is 2. So add the 2 zeros after that, 200. Again, there are no units. Our units cancel. So when we work backwards, we keep the units. So that should have been newtons, this is newtons. 2,000 newtons. Again, both of these answers were already in significant figures, so we're good. All right, if you need more example problems, let me know. I have some. I'm more than willing to write them up and work them out with you guys. Just send me an email, send me a response to this video, however you want to communicate to me, please do it. Thank you.